Welcome to chapter 26. We're going to talk about the human eye and a few optical instruments along the way. So in the book, it points out that the human eye, the outer layer of it is the cornea, and the cornea has the power of 43 diopters. Remember from the last chapter that capital D stands for diopter. One diopter is 1/1 meter. So remember, power is the inverse of the focal length. The crystalline lens, which is inside the eye, has a power of anywhere from 20 to 33 diopters. So both of these, the cornea, which is the outer layer of the eye, and the crystalline lens, which is inside the eye, act like lenses to bring objects into focus. So if we look at our diagram, you can see that here's the outer layer, it's the cornea. There is a space directly behind the cornea that's full of something called the aqueous humor. Then there is an opening in the iris called the pupil. The pupil is that black spot in the middle of your eye that opens up in dim light and closes down in bright light. And behind that is what we refer to as the crystalline lens. It's attached by the ciliary muscles that keep it in place, and the ciliary muscles also change the curvature of the crystalline lens. When it's completely relaxed, it's as thin as it can get, and when you use your ciliary muscles, you can make it rounder. So we can change the shape using the ciliary muscles. Behind the crystalline lens is an area that's full of something called the vitreous humor. And then on the back of the eye is the retina. The retina is where light comes to focus. There are receptors on the retina for light. They take the information and transmit it along the optic nerve to the brain, and then you process it. The spot on your brain, on the retina, the spot on the retina where you have the highest concentration of receptors is called the fovea. And the spot on the retina where there are no receptors, because that's where it links to the optic nerve, is called the blind spot. So if we scroll down, whoops, I went too far again. I have a bad habit of doing that, don't I? So when we look at this, there's a reminder that one diopter is 1 meter to the -1. And it emphasizes what having a power of 43 diopters would mean for the focal length. It would be about 23 millimeters, which is roughly an inch. The human eyeball is a little bit more than an inch front to back, so that makes perfect sense. So the average size of an adult human eyeball is about 25 millimeters. And since 2.54 centimeters is an inch, 25 millimeters is approximately an inch. All right, so if we come up, so we point out that incoming light passes through the cornea. That's that transparent membrane on the outer part of your eye. And like I said earlier, it acts like a lens. The aqueous humor is viscous, it's jelly-like. It fills in the space, it holds the eyeball in place, but it does very little bending of the light. The light then travels through the pupil, and then it's bent in the crystalline lens. Again, that is sort of jelly-like. It can change its shape using those ciliary muscles, and it's ever so slightly yellow in color. I'm sorry about the pause. The reminder came as a surprise for me. So it's ever so slightly yellow, and it's made out of fibers that slide over each other to give it that change in shape when you exercise those ciliary muscles. Behind the lens, that cavity is full of the vitreous humor. Again, it doesn't do much to bend the light. It just holds things in place. And then we've mentioned that the light's focused on your retina. It has receptors For black and white vision and for color vision receptors are called cones. Black and white receptors are called rods. And not all creatures, great and small, see things exactly the same way. Reptiles and birds and humans and primates have color vision. Other mammals do not, or at least not the same way we think of. Every day we learn a little more about this. If an animal is active during the day, it's really important for it to have good color vision. If it's active at night, then color vision is not as important as having that light-dark sensitivity. Color blindness is a sex-linked trait that is passed on usually from mother to son. The most common form is a red-green color blindness. It means that your color receptors don't work the way they should. And so you may see things in shades of gray that someone else sees in shades of, say, red or green. So for example, in this little circle, and there are lots of them online, you could Google color blindness test online and come up with all kinds of things. There's a number buried in the little circles inside. If you can see the number, you're not colorblind. If you can't see the number, you might be colorblind. Insects see the light in the ultraviolet range. And so the flower on the left might be what it would look like in daylight. And on the right, it would look like this in UV light. So all yellow flowers don't look the same to insects. All white flowers don't look the same to insects. We've mentioned the fovea already. It's the place where there's the highest concentration of receptors, in particular cones. Remember, that's for color vision. You don't have cones on the outer edges of your retina, and what that means is that on the outer edge of your retina, you can perceive black and white, so motion, long before you can tell the color of something. If you've gone to the optometrist or the ophthalmologist, they may have done a little test to check your peripheral vision just to be sure it's in good working order. People who have glaucoma lose their peripheral vision slowly over time. So we've mentioned the blind spot also earlier. It's where the optic nerve connects and takes those receptors. The optic nerve takes that information, sends it to the brain, and your brain analyzes it. And what it will do is actually invert the image. We've mentioned in class that the image on the retina is inverted. And so your brain learns early in your life to flip the information. That's kind of a neat little feature of your brain. As I've said earlier, your eye acts like it's made out of two lenses. The cornea acts like the first lens, and then that crystalline lens inside the eye fine-tunes the image. The cornea does the most of the bending or refracting of the light. Accommodation is the name we give to the process where your crystalline lens changes shape to bring something into focus on your retina. So light comes from the top of the object, enters the eye, gets bent, forms the image of the top. Light comes in from the bottom of the object, enters the eye, gets bent, forms the bottom of the object. And by virtue of the shape of the lens, what you end up with is an inverted image, which your brain has to then flip to make any sense out of the world we live in. When your lens is as thin as it can be, your eye is relaxed and distant objects will come to focus on the retina. When your eye is as fat as it can, when the lens is as fat as it can be, you're using those ciliary muscles to round it out. And we do that when we want to bring something that's close to us into focus on the retina. So you need a fat, rounded lens for close focus, a thin, flatter lens for distant focus. And these two little diagrams just show that. The top one is for something very far away, and the bottom one is for something much closer. And you can see very far away, the crystalline lens, which is this white oval, is thinner. Close up, the crystalline lens, which is this white oval, is fatter. Different materials have different indices of refraction. We mentioned that in a previous chapter. Water is 1.33, air is 1.0. You notice we're rounding off. But you should also notice that the cornea and the aqueous humor and the crystalline lens and the vitreous humor all have a similar index of refraction. So they all have the capability of bending light a similar amount. There are different kinds of vision defects. Nearsightedness is called myopia, and that's when you can see things that are up close, but you can't focus things at a distance. People who are nearsighted oftentimes can read a book, but they can't read the clock across the room. There are two reasons this can happen. It can be because the eyeball is too long for the lens, so the distance between the crystalline lens and the retina is too far, or it can be that the crystalline lens is just too fat for the shape of your eyeball. In either case, the object that you're trying to focus on comes in focus in front of the retina, and as you try to push it back, you can see near objects, but you can't ever make your lens thin enough to focus those distant objects. We would correct this with a diverging lens. That would spread the light out a little bit so your crystalline lens could bring distant objects into focus. And there's a little graphic showing you what's going on with the lens and focusing things. Farsightedness, sometimes called hyperopia, is the opposite of that. You can see things at a distance, but you can't see things up close. And again, this can be either because your eyeball is too short, the distance between the crystalline lens and the retina is not long enough, or because your crystalline lens is so thin, you can't ever make it fat enough to focus things that are up close. And for this, the way you correct it is with a converging lens. So people who are farsighted can see the clock across the room, but they can't read a book without corrective lenses. And again, a little graphic, which is in your notes to help you see what's going on with the object and the lens. This graphic shows the difference between myopia and hyperopia, between being nearsighted and farsighted. Remember, people who have myopia are nearsighted and they can read a book, but not the clock on the wall. Hyperopia, they can see that clock on the wall or the leaves on the trees outside, but they can't read the book without corrective vision. Presbyopia or presbyopia is farsightedness brought on by an increased age. What happens is the crystalline lens becomes rigid over time. It loses its flexibility. And so your ciliary muscles, which are necessary to bring near objects into focus, you have to round out that lens. The lens can't round out because it's more rigid than it ought to be. And so as time goes by, normally people will notice that it's harder and harder to read things. Typically in your 40s or 50s, you discover this and you'll see people holding things farther away. And then finally they have to bite the bullet and buy those dime store glasses, the glasses you can get at Walmart or the drugstore. Some people call them readers or cheaters to help you read. And then eventually some of us just have to buy glasses because all of our vision has gone to crap, as it were. All right, so a lot of people become farsighted as they get older. It's very common. Another vision defect is astigmatism. So astigmatism is when there are parts of either the cornea or the lens inside the eye that are not uniform. And so light comes to focus at different places. A typical test for that is this diagram. where if you cover one eye and look at it, if you have astigmatism, some of the lines look darker than others. Parts of your field of vision are sharper, and that's the part that will appear darker. Parts of your field of vision are a little fuzzy because of this lack of uniformity, and it will appear a little light gray compared to the other areas on this. Can be corrected with special lenses designed to compensate for that lack of uniformity. One symptom of being astigmatic is that as you're reading, if you have a lot of trouble staying on the line when you read, you may have astigmatism. It's one of the early signs of it. Another vision defect that's quite common are cataracts. Cataracts are discolorations or a cloudiness in the crystalline lens. Usually, if a cataract has gone too far and you look at someone, it looks like they have a white spot on their eye. The nice thing is that these days we can do relatively easy surgery to correct for cataracts. They make a little incision and go in and remove the crystalline lens and replace it with an artificial lens. Normally, people who have cataract surgery don't need corrective lenses right away. They may tell you that their vision is like they were 20 years old. In some cultures, cataracts are more common at an early age. In India, it's more common to see people in their 40s with cataracts, whereas in the United States, it's usually people in their 60s and 70s that have cataract surgery. One thing you can do to cut down on your likelihood of developing is to wear sunglasses early and often. So again, a normal eye and an eye with a cataract. Again, it's a drawing, so it's not quite the way it would look in real life. Another vision illness is glaucoma. Glaucoma is damage to the optic nerve, and we assume it's caused by increased pressure inside the eye, which destroys some of the connections on the optic nerve. And what you end up with is developing what's referred to as tunnel vision. You have vision in the center of your field of vision, but you begin to lose your peripheral vision. Normally, if you have glaucoma, if they catch it early, they can do things to help reduce that intraocular pressure, which is why we ought to have our eyes checked periodically. Even if you don't need glasses by the time you're an adult, probably you ought to have your pressure inside your eye checked every 4 or 5 years, even if your vision is just fine. Diabetic retinopathy is another issue. This is quite common in people with diabetes. And so if you are diabetic or you know someone who is, again, you need to have your insulin well regulated, and you need to see an ophthalmologist or an optometrist on a regular basis. Some of the signs of diabetic retinopathy are blurred vision and floaters and flashers and sudden loss of vision. And there are ways certainly to correct it, but the best approach is to monitor your insulin level and keep it well within the levels recommended by your physician. And yet, one more vision defect is age-related macular degeneration. It's becoming more and more common, and we're developing treatments for it. There are two types, the wet and the dry, and you can certainly read about it. Again, it's one more reason why people at least after the age of 50 should have their eyes checked by a medical professional on a regular basis. You notice in the little photograph that age-related macular degeneration is sort of like the inverse of glaucoma, where glaucoma, you lost your peripheral vision and kept your central vision. With age-related macular degeneration, you lose your central vision and keep bits of your peripheral vision. But with both of them, we want to prevent it. You can see that there are some things that increase your risk. And there's a little chart, an Amsler grid, that helps you decide, are you losing parts of your field of vision? And you can certainly Google it if you're curious. We will stop the share for now and stop the recording.